CV before. He's from Institute of Sustainability Science from Vietnam Japan University, VNU. Her research area and expertise is about solid state physics, condensation physics, matter physics, and doing computational his research and her expertise. So please enjoy her lecture. To Dr. Phung, time is yours.
Thank you. Shall I share my screen?
Yes, please, Doctor.
Thank you. Thank you very much for your introductions. And at first, I'd like to take this opportunity to thank the organizer for giving me the chance to present about my current research. And thank you very much. So let me start my talk. The title of my talk today is Gas Adsorption on Surface of Graphene and Graphene on Substrate. Um, Here's the outline of my talk today. Uh, my talk will divide it into four parts. The first, I would like to give an introduction about graphene-based gas sensors for toxic gas detection. The target I would like to show here is including the carbon oxides, ammonia, and nitrogen oxide. The substrate I use in my study, including the precene graphene and also graphene on the hexagonal boron nitrides and graphene on the silicon dioxide. And next to that, I will give a brief introduction about the computational details. Then I would like to show you some current result and discussion. And finally, I will conclude my presentation. So let me start my talk with the introduction about graphene. I believe maybe all of you already know about these materials. Single layers of graphene is actually a single layer of graphite that's formed by repeating the hexagonal lattice. This has been great interest for the science community since it was the first and ambiguously identified in 2004 by the group of Professor Graham and Professor Novoselov. And actually, they got the Nobel Prize in 2010. And I briefly here with some properties of these two-dimensional materials. Graphene, you know, it has been considered as a very promising material for flexible and also transparent electronics application. Thanks to its extraordinary electronics and mechanical properties, resulting in from a perfect hexagonal crystal lattice. Two-dimensional materials. And graphene can be considered as a starting point for many nanographite devices. However, it is very challenging to make the graphene into nanoelectronic devices due to the mechanical instability of freestanding graphene layers being placed on the substrate. So recently, the attempt to assemble the graphene layers on top of silicon dioxide, for example, and gallium arsenide or some other material like hexagonal boron nitrides has been widely studied to demonstrate the possibility to enhance the electronics and even the optical properties of graphene. And in my research, I use two kind of substrate. The first is the hexagonal boron nitrides and the silicon dioxide. As so in the figures, this figure shows demonstrates the topography of graphene on the hexagonal boron nitrides, and here is for graphene on the silicon dioxide with the image of charge density map like this, the latter image. And from the point of view of computational detail, we should look at the lattice mismatch between these two materials. And by calculation, we have found that the lattice mismatch of these two graphene on these two substrates with hexagonal boron nitride, the lattice mismatch is equal to 1.78%. And for the case of silicon dioxide, that value is 0.48%. So some this kind of two-dimensional material also we call is the van der Waals heterostructures, because the interaction between these two layers is like physical interaction, and another name is we call it the van der Waals heterostructures. So the target, the objective of my research is the first is we would like to investigate the interaction between graphene and the different substrates to design the material for gas sensors. And secondly, we would like to know the adsorption mechanism of the toxic gas when they adsorb on these heterostructures. And finally, we would like to know the enhancement of selectivities and sensitivity of this material for gas sensors based on these materials. So here I would like to introduce about the computational details. In our research, we use the first principle DFT calculation, which is implement using the vast program package with the PA double pseudopotential. We investigate the system by applying the three different types of van der Waals functional, which is the first is the REP PBE, that is the original van der Waals functional. And the second one is all PBE, which is developed to make the more get more accuracy to describe about the interaction in the physical adsorption material system. And the last one is van der Waals DF2, which was developed by the Professor Hamada in Osaka University to also to improve the accuracy of the system. And I would like to introduce here one important tool which is developed by Dr. Dinh Van An in Vietnam Japan University and also Osaka University, which calls the computational DFT-based nanoscope to develop this tool to overcome the problem of finding the minimum energy configuration and reduce the computational costs. Using this tool, we can estimate the response of the surface on the substrate, and also we can scan horn of the surface to find the minimum energy configuration of the toxic gas when they adsorb on the two-dimensional materials. And finally, using this tool, we can calculate the adsorption energy in the same configuration. That means it can increase accuracy. So let we demonstrate these two on these figures with treating the we using these two we consider the gas molecule at a tip of a scanner here. By which the molecule will move on the adsorbent surface and rotate around its center of mass to find out the stable adsorption configuration. And at each configuration, we will apply the DFT simulation to find the total energy. And so the minimum energy configuration will be determined. And not only on the like a parallel rotation, but we also can vertical shift to find the optimized structures. Okay, let me move to the part of result and discussion with the main four results. The first is about the optimization structures of graphene on these two substrate material. And then the adsorption configuration when the toxic gas adsorb onto the surface of graphene put on this different substrate. And next to that, I will show the result on electronics properties, including the band structures and dose analysis. And finally, is some other properties like charge transfer or the tensile effect. Okay. Here I shown in these figures. The first is when we put the graphene on HBN and we using the scanning tool to find the minimum energy configuration when we put the graphene on the HBN. And this figure shown these figures. Sorry. So as I have been mentioned before, when we want to find the stable structure of graphene put on the substrate, at first we are shipping the graphene layers in the horizontal translation, while we keep the substrate, in this case, a hexagonal boron nitride. And when we shift in the direction of X and Y axis, we can get the energy profile in this, like in these figures, which show the color indicate the difference in the binding energy in this system. The dark blue color show the lower energy configuration. On the other hand, the red and the yellow color show the high energy configuration. So based on this one, we can determine the minimum energy configuration in the X and Y axis. Then we move the vertically on the along the z-axis of the supercell, and the result show in these figures with the binding energy depend on the distance between these two layer materials. So we apply here with the three different van der Waals functioner, which is the original uh, red PBE and op PBE and DFT DF2. Sorry, I made mistake here. It's not D2, it's DF2. And the result shows that the around 3.2 angstrom, we can get the minimum configuration of graphene on HBN. And the binding energy is around 1 eV. And the figures shown here with the graphene put on the boron nitride like this. In the case of silicon dioxide, the result has been shown here with the local minimum, and similarly about 3.5 angstrom, we get the stable structure of graphene on the silicon dioxide with also the binding energy in the range of 0.8 to 1 electron volt. This result shows that the graphene is weakly bound to the hexagonal boron nitride and the silicon dioxide surface, and they have the binding energy is around 0.8 to 1 eV, which is typical for the van der Waals heterostructures at the distance about 3.2 and 3.5 angstrom. Next to that, we analyze the band structures and dose of these materials. The results shown here with the system of graphene on HBN on the left-hand side and the graphene on silicon dioxide on the right-hand side. The important point we would like to focus here is the graphene, freestanding graphene have the zero band gap. However, when we put the graphene on the substrate, it appears the narrow gap of graphene. In this case, on the case of graphene put on the hexagonal boron nitride, the gap is opened about the 15 milli electron volt. In the case of silicon dioxide, this value is 120 milli electron volt. So the interaction between the graphene and this substrate with the pi and pi star state of the carbon atom in graphene is break the symmetry of graphene, and then is occur the small band gap at the Dirac point, and the new band originating from the substrate modify the band gap, the band structure of the breathing graphene, and open the gap about this amount, 50 milli electron volt in the case of graphene on hexagonal boron nitride, and in 120 milli electron volt in the case of graphene on silicon dioxide. So after getting the stable structure of graphene on this substrate, we move to the next to investigate the adsorption by investigate the toxic gas. We consider 5 toxic gas, which is a carbon monoxide, carbon dioxide, nitrogen oxide, nitrogen dioxide, and ammonia. This figure shows the minimum energy configuration of toxic gas adsorption on graphene when we put graphene on the substrate of boron nitride. And as you can see here, all of the gas molecule has a parallel orientation with the respect to the planar surface of the proteins graphene and also the graphene on boron nitride. And by calculate the binding energy, in this case we call it the adsorption energy, we found that these molecules are weakly bound to the substrate, and having the adsorption energy which is typical for the physics adsorption. In the case of silicon dioxide, the gas adsorption configuration shown here, different with the boron nitride. When we put the graphene on the silicon dioxide, the graphene has been changed in the geometrical structures. It's not planar like this. Mm, to compare the effect of substrate on the adsorption energy, we put the value of adsorption energy on these figures to compare between three cases with the gas adsorption on the protein graphene with the gray colors, and then the green color is the adsorption energy of gas on the graphene on the substrate HBN, and the brown one which represent the adsorption energy for the case of gas when we put on the silicon dioxide. And you can see that in general, when graphene associate with silicon dioxide, which will help to improve the sensitivity for detecting this toxic gas better than HBN. About the sensitivity, so NO2, in the case of NO2, it seems this gas molecule adsorb is better than for others because they shown the very, compared to other NO2, the adsorption energy is much higher. However, it's not clearly about the selectivity because the adsorption energy is not improved. So we need the further investigation on this selectivity. To look deeper in the changing in electronics properties of this adsorption system, we analyze the band structure and density of state. The results shown here for the case of carbon oxide adsorption on the graphene into the boron nitride. On the left-hand side, which shown the band structures. On the right-hand side is the density of state of the substrate of the carbon graphene on HBN and the CO gas, and then the density of state of the total. And I would like to focus here. The dots show the energy level of the LUMO for the CO with the 2-pi state and HUMO with the 5 sigma state. And the results show that for the adsorption, because it's a weak physical adsorption, so the difference in energy between the LUMO and HUMO is not so different between before and after adsorption. However, the LUMO beyond the Fermi level, indicating that this CO molecule will donate the electron for the substrate, for the graphene on the substrate. Similar thing for the case of CO2. And look at in these figures, uh, the distance between the HUMO level and the Fermi levels is higher for the case of CO. So we also can predict that the tendency that the CO2 also donates the electron for the substrate. However, the amount of charge transfer will be smaller. To um, to calculate in detail of the charge transfer, uh, sorry, in this slide, I would love to show the effect of the substrate on the graphene. So this figure uh, shows the change in density of state of graphene which have interact with the toxic gas. On the right hand side, uh, is for the case with the adsorption, and the left hand side is before adsorption and after. And also this carbon graphene is far from the toxic gas adsorption. So the difference between two figures is about the orbital contribution to the dose of graphene. So the py orbitals and more px orbital appear on the carbon graphene which have the interacts with the gas molecule. On the other hand, the adsorption of these considered gas molecules cause the hybridization between the molecular levels and graphene valence bands. So this is explain the reason why the interaction of toxic gas and also the effect of the substrate which break the symmetry of graphene, and that's why the band gap occur at the direct current. Okay, so to look more deeply in the charge transfer amount, we calculate the Bader charge of each system, and the result has been summarized in these tables. For the comparison purpose, the first one is for gas on the freestanding graphene. And the second one is for gas adsorption on graphene on the HBN substrate. And the last one is charge transfer between the gas molecule to graphene in the case of graphene put on the silicon dioxide. And you can see easily that charge transfer results show the toxic gas acts like a donor on the graphene and the graphene on substrate. That means by introducing the different substrate, which is the HBN or silicon dioxide, there's enhancement of a sensitivity of graphene base towards the gas molecule, and the amount of charge transfer is increased. In these figures, we shown the charge density difference induced by the adsorption of the case of NO gas molecule on graphene HBN. The figure demonstrates the electron donation. So the electron loss, the loss of electron is indicated by blue one, and the electron formulation is indicated in red. And in totally, as I shown before, for the case of NO, the charge transfer for the case of NO adsorb on the graphene on the boron nitride is about 0.05 electron. The amount is quite small. And the result also shown that the direction of NO when they adsorb on the graphene surface, which is a oxygen atom is close to the graphene surface, and that's why the graphene gained the electron mainly from the oxygen. Another result I would like to show you, which is about the effects of tensile stress. And this figure shows the result with the graphene on the boron nitride heterostructures by applying the tensile effect. We found that the band gap of this system is changed. So ordinary graphene on the boron nitrides, the band gap is about 50 milli-electron volt. However, when we stretch out this, the gap is changed. In the case we apply the tensile is a minus value of -5 or -10, the band gap is open bigger for 67 milli-electron volt for the case of -5%, and for -10%, the band gap is open larger at 85 milli-electron volt. However, when we apply the tensile of 5 or 10, there are no gap, and it's become the metallic band. We also tried for the case of adsorption gas on the graphene on substrate by applying the tensile effect, and we found that it's also changed in the electron transfer, which is also indicated in the band structure endorsed and also in the charge difference when we demonstrate. Okay, so I would like to conclude my talk with some brief summary. Like at first, we have studied the adsorption of toxic gas molecules in the graphene on different substrates of hexagonal boron nitrides and silicon dioxide. And we found that this toxic gas molecule adsorb on these materials belong to physical adsorption at the distance in the range of 3.2 to 3.6 angstrom. The band structures and density of state results so that the interaction between graphene and substrate has been break the symmetry of graphene and appear the narrow band gap at the direct point. And we also discuss about the enhancement of sensitivity and selectivities, which we can conclude that by putting graphene on the substrate, we can enhance the sensitivities. So that means we can use this for the gas sensing devices application. In the future work, we are going to continue to investigate the enhancement of selectivity of graphene by introducing the different substrates with the two-dimensional materials which is gallium arsenide or S and another materials, or defect or doping the transition matters on graphene. So this is my final slide in my talk. Thank you very much for your interaction, for your attention.
Thank you, Dr. Pung, for your nice and interesting lecture. Now it's time for a question session. Here on the chat box, we already have at least three questions. The first question comes from Melsa. She's asking, what were your consideration when you choose the van der Waals functional in your research?
Yes, so I will answer one by one.
Yes. The first
Okay.
question is, what were your considerations when you choose the van der Waals functional in these calculations?
Yeah, thank you for your question. So, as I mentioned at the introduction, because the absorption of this gas on the okay, let me make clear. So actually, there are two kind of interaction in the material in my uh, research. The first one is when we put graphene on the substrate, and graphene on the substrate is kind of the interaction between these two layers is a weak physical absorption. And also for the gas molecule, when we absorb on the graphene, is also belong to the physical absorption. That means mm, um, the sorry, that means I would like to uh, the I think there are two reasons to select the absorption at the distance about more than 3 angstrom. There are no chemical bonding, and the stacking between the two layer materials uh, shown the very weak physical absorption. So I think that is the reason why we apply the weak van der Waals interaction.
Okay. Hope the participant can get your answers. And we go to the second questions. Uh, he's asking, graphene on boron nitride substrate is a non-activated similar to the other one, but he thinks that he didn't see the PC sorption at the initial graph. Could you explain why?
Hello.
Oh, yes,
Hello.
yes,
Could you please repeat the question?
yes. The questions. Uh, he's asking that graphene on boron nitride substrate
Mm-hmm.
is is a non-activated similar to the other one.
Mm-hmm.
But he thinks that he didn't see the physics option at the initial graph.
Initial graph.
Yes, probably in the first result you show us here.
Yes.
So he thinks that he did it is not physics option.
A physics
Uh,
option.
Yes.
Pak Fazzi, Pak Fazzi, could I explain
Oh,
a little bit more about my question?
yes, please.
Dr. Pung, thank you very much for your nice slide. Yes, this chart is my question. We can see that at the initial, for instance, the CO gas coming through the surface of hexagonal BN. Normally, at the initial, we can see the what they call it, the increasing of the energy level, and then go down to the chemistry option as at the left side.
Yeah.
In this chart, I couldn't see the physics option of CO or CO2 gas interact before coming through the surface. That's the question actually.
Okay. So, okay, thank you for your questions. So, can you see my slide? This one?
Yes, of course.
Okay. So, let me explain first. I wish I, I hope I understand your question. So, at first result, in this case, there are no gas absorption only when I put the graphene on HBN, and I would like to find the minimum configuration minimum energy configuration. So this figure shown the binding energy depend on the distance between two layers. So this distance, that means from 2, 3, 4, 5 angstrom, that is the distance between the graphene and HBN. And by moving the graphene on the HBN, we calculate the binding energy showing here. So about the less than 3 angstrom. So uh, which shows the very high energy configuration. And then we increase distance and the energy is increase again. So in this figure is just we would like to show the binding energy between the graphene and HBN. And for the case when we absorb the gas molecule, for example, CO, and the process, we did a similar thing by the when we put CO on the graphene on substrate, we also rotate and translate that molecule on the graphene surface. And then in each point, we calculate the total energy. And then also we move that molecule far close and far from the graphene and sorry, I do not show here, but the energy profile will be similar. And the results, we can get two results here. The first is about the distance, and the second is about the binding energy. And sorry, I do not show the figures of the, but I summarize here for absorption energy. For example, for the case of CO, the absorption energy is about 0.6 0 0.1, maybe 16 or 17 EV, and the distance also about 3.5 angstrom, I think. And based on these properties of the absorption energy and the distance, we can conclude, and it's shown the gas molecule is the physics absorbed on the graphene on the substrate. I hope I can get the point you question. Yeah, that is.
Okay. Thank you very much for your hello.
Hello.
Oh, okay. Maybe we go to the another question from another participant. Someone asks about the configuration of your graphene on boron nitride substrate. How to decide that your structure is stable on the substrate?
Yeah,
How's
yeah.
how is the stability of graphene on the substrate?
Okay. So, so as I told you, we at first, um, we calculate the lattice mismatch of between the graphene on HBN. And after define the mismatch, we change the lattice constant to put in the simulation. And here you can see when we put the graphene on the HBN, we should find the appropriate position to get the minimum energy. So let me explain again by using the DFT-based nanoscope tool, which is developed by Dr. Dinh Van An. And we consider the upper layer, which is graphene, layer tip, and the lower layers, which is a keep stable. And then we rotate and we move in horizontal and also vertical translation of graphene on the boron nitride. And the result shown here, this result shown when we move the graphene on the horizontal translation of boron nitride to find the minimum energy configuration here. And then we, by the z-axis, we move the graphene vertically. So by combining between two results of shown in these figures, we can find the minimum energy configuration of graphene on the substrate, like in this case is HBN. Yes,
Here
so I hope I
here
can get
you follow the lattice constant of substrate. So
yes,
you
both lattice constant and also change the different different possibilities
mm,
which graphene can lie on the boron nitride.
so the graphene you create here use lattice constant of boron nitride.
No. Okay, I understand the very technical point that, as I shown before, The mismatch, lattice mismatch between graphene and boron nitride is about 0.78%. So to create the cell with the graphene put on HBN, we take uh, the summary of the two lattice constants of both graphene and boron nitride after optimization, and we divide into by 2.
Ah,
Yeah. So using that lattice constant, we will uh, optimize the both again the lattice constant and also the distance between the graphene and boron nitride. Also another possibility of when we ship the graphene on the boron nitride substrate.
so the lattice of graphene is a little bit bigger.
Modify, yeah, we modify. Yeah.
Okay, it's related to the next question actually. Okay, you already answered that. So the next question is about the electronic properties. So you show us that there is a band gap opening while you apply stress and strain. So why does the gap open here?
Yeah, thank you. And actually, this link to the previous your questions. I think when we apply the tensile stress, which is for the minus values, that means that we compact the materials in the three-dimensional, both the X, Y, and Z. So the material is become contract, uh, and on the other hand, with the positive tensile, that means we expand the lattice constant of the unit cell. So it changes also in geometrical structures.
Mm, okay. Hello.
Yes.
Okay. Thank you for your answer.
Yeah, thank
I
you.
think okay. Is there any more question from participants?
Hello.
Oh yes, please. You can ask directly.
Yes. Dr. Bach, I
Yes.
that the bandgap has not opened very hard. I think very hard. The bandgap is important.
Your voice is not.
Clearly. Hello. Can you hear
I'm
me?
sorry. Your voice is not clear.
Okay. Now. Okay now.
Dr. Phung, can you hear the questions?
I'm sorry, I cannot hear the
Y-
question clearly.
yes,
Okay.
I also cannot hear the voice.
Can you hear me now?
Yes,
So my question is, I do not think that the band gap open,
I see.
possibly because of the low sampling of K-point.
Okay,
You think?
okay.
Well,
Uh, Dr. Pung,
Yes.
uh, participant asking about the
The band gap
band gap
opens, right?
open. Yes,
And yes,
he thinks
actually,
that it's due to the K point sampling in your calculations.
I don't think so because we have tests with the many different K-point sampling, and the calculation has been tested firstly for the uh, freestanding graphene, and we confirmed the result of the zero band gap of graphene. Then after that, we expand the to um, the effect from the substrate, the 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 band generate from the substrate modify the band which is the contribute for the gap at the direct point. And we compare our result with experiment data. And in experiment, it has been observed that the open band gap of this system in the from 30 to 60 milli electron volt. So I believe that we can compare our simulation model with the experimental data because I think we have been test and we used enough the K-point sampling, and that's why in the tensile effect calculation we try with the different lattice constant, and the results shown the um, band gap opening, and I think that is not we believe in the accuracy of our calculation. That is.
Okay, thank you, Dr. Peng. I guess we already reached our lecture time. If I may, could you turn on your video, Dr. Pung?
Ah, yes.
We would like to hear your
Hello.
okay. So uh I'm not so sure. Maybe one of my colleagues already take our picture.
Okay.
Okay. Thank you, Dr. Pung, for
Thank you
your
very much.
lecture and research here you present to us. So for all participants, I think this is our end of today's